Hello everyone, I'm Nagayasu from Okayama, Japan. Now I talk about performance evaluation of sinusoidal flux reluctance machine for improving power density with reduced torque and input current ripples. Recently, electric vehicles are widely used. For the vehicle proportion of high-cost EV, permanent magnet machines such as RPM SM are widely used because of high efficiency. However, these machines are expensive because they contain the permanent magnets. On the other hand, for low-cost EV, reluctance machines such as SRMs and SynRMs are attractive because these machines don't have any permanent magnet. So they have high thermal tolerance and high cost effectiveness. So far, SRMs and SynRMs have been investigated as a reluctance machine for vehicle propulsion. However, these machines suffer from some issues for vehicle application. The SRM is driven by square inverter current with 3 H-bridge inverter. This leads to the cost up. Furthermore, SRM generates large input current ripples and large output torque ripples. These ripples generate battery deterioration and noise vibration. Then, the SynRM have the sinusoidal inductance profile and the star-connected windings. So the phase magnetic flux contains the third harmonics and peak flux is large. This generates the magnetic saturation and reduces maximum output torque. As a result, this leads to the small power density. In this slide, I explain the sinusoidal flux reluctance machine proposed in the previous study. The principle is similar to the SynRM. This machine has sinusoidal reluctance profile and delta connection. This machine driven by sinusoidal magnetic flux, unlike SynRM. By them, the input current torque ripples and output torque ripples are suppressed. Furthermore, the magnetic flux has small peak flux and moderate slope. So, this machine can output high torque at high rotation speed, and this leads to improvement of power density. However, the phase current contains the third harmonics. So, this machine circulates the harmonics in delta connection. Therefore, the three-leg inverter can be applied. As a result, the sinusoidal flux reluctance machine solves the issues of conventional reluctance machine. In this slide, I explain the purpose and approach of this study. The basic operating principles of this machine have been confirmed in the previous studies. This figure shows prototype rotor and stator. However, we can't evaluate and compare this machine with SRM and SynRM by 3 points. Therefore, we did 3 approaches to design optimization. In this slide, I optimized the number of turns of stator. The SynRM has star connection, and sinusoidal flux reluctance machine has delta connection. So each impedance from bus line is different. Therefore, to equalize the impedance, the number of turns of sinusoidal flux reluctance machine has the square root of 3 times more than that of SynRM. At that time, SynRM has 14 turns. So, the number of turns of sinusoidal flux reluctance machine has 24 turns. Next, we optimize the rotor geometry to reduce the minimum reluctance. In this slide, I explain the gap length for the prototype and novel rotor. This equation is gap length of prototype. This equation is gap length of the novel rotor. The gap length of novel rotor is prototype equation plus the second harmonics. This figure shows comparison of both gap lengths of aligned position. This figure shows comparison of reluctance, calculated novel rotor and pure sinusoidal. At aligned position, changing gap length of novel rotor is smaller than prototype rotor. This means the minimum reluctance of novel rotor is smaller than that of pure sinusoidal. In simulation results, ripple ratio of the novel rotor is larger than prototype rotor. However, novel rotor's RSM value of phase current is less than prototype rotors. Therefore, novel rotor is expected to reduce copper loss. Next, we decided appropriate the ratio of reluctance profile. The typical power losses are copper loss and iron loss. Copper loss comparison RMS value of phase current squared. Iron loss comparison RSM value of magnetic flux squared. This figure shows phase current waveform and magnetic flux waveform of sinusoidal flux reluctance machine and SIN-RM. Each magnitudes are different and depend on the ratio of Rmax to Rmin. Therefore, the ratio is major factor for determining power losses. So we analyze the dependence of power losses on the ratio of Rmax to Rmin. At that time, Rmin is fixed and Rmax is changing. This figure shows a variation of each parameter with respect to the ratio of Rmax to Rmin. Vertical axis is the ratio of sinusoidal flux reluctance machine to SIN-RM. Horizontal axis is the ratio of Rmax to Rmin. Peak flux is decreased as the ratio of Rmax to Rmin is large. Therefore, sinusoidal flux reluctance machine can improve power density. However, RMS value of phase current is increased as the Rmax to Rmin is large. Therefore, copper loss is increased and iron loss is decreased. Optimal ratio of Rmax to Rmin at SIN-RM of is 3:4 because copper loss and iron loss are almost same. Therefore, we compare sinusoidal flux reluctance machine and SIN-RM at the ratio of Rmax to Rmin, where their total losses are almost same. From this figure, the total losses of both machines are almost same for the ratio of 3:4. So we designed the novel rotor so that the ratio of Rmax to Rmin is 3:4. This slide shows all design rotor geometries. All rotor geometries are constructed by changing a rotor of commercially available SRM. This shows specification of SRM and cross view. This figure shows design rotor model and reluctance profile. The figure on the right is enlarged view of reluctance profile. From the figure, the ratio of Rmax to Rmin in sinusoidal flux reluctance machine and SIN-RM are almost same. Therefore, we optimally designed the sinusoidal flux reluctance machine. This slide shows experimental setup. The purpose of this study is to compare and evaluate sinusoidal flux reluctance machine with SRM and SIN-RM. This figure shows experimental rotors and motor test bench. This figure shows the inductance profile of each machine measured at 14 turns. Under their condition, we evaluate input current, inverter current, magnetic flux, and output torque. This slide shows the experimental result of operation at 1 Nm. This figure shows phase current waveforms of 3 machines. This figure shows magnetic flux waveform of 3 machines. Comparing peak magnetic flux, the sinusoidal flux reluctance machine exhibited the smallest peak flux among 3 machines. This figure shows input current waveforms, and this figure shows torque waveform of 3 machines. Comparing input current ripple ratio, the sinusoidal flux reluctance machine exhibited the smallest ripple ratio among the 3 machines. Also, the sinusoidal flux reluctance machine exhibited the same torque ripple ratio to SRM. The issue of the sinusoidal flux reluctance machine is larger copper losses. Hence, in this slide, we compare copper losses at each torque of 3 machines under their conditions. This figure shows the result. In high output torque region, copper losses of CRM change steeply. So this region is magnetic saturation region for CRM. The reason for this result is peak magnetic flux of CRM is larger than sinusoidal flux reluctance machine. Therefore, copper losses of CRM is large. This result supports that the sinusoidal flux reluctance machine can improve the power density compared with the CRM. This slide shows the summary and conclusions. Thank you for your kind attention.